Let me show you how to be a good Bayesian.
My guest today is Gabriel Stechschulte, a software engineer passionate about probabilistic programming and optimization. Gabriel recently re-implemented BART, Bayesian Additive Regression Trees, in Rust, making the algorithms faster, more flexible, and more suitable for real-world applications. So if you are a PyMC BART user, I definitely recommend checking out his implementation that is in the show notes. In our conversation, we dive deep into what makes BART special, its ability to quantify uncertainty, handle different likelihoods, and serve as a strong baseline in settings like optimization and time series. We also explain how BART compares with Gaussian processes and other tree-based methods, and talk about practical challenges like handling missing data, integrating BART into PyMC, and embedding machine learning models into decision-making frameworks. Beyond the code, Gabriel reflects on open source collaboration, the importance of community support, and where probabilistic programming is headed next. This is Learning Bayesian Statistics, episode 142, recorded September 18, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com. Gabriel Stechschulte, welcome to Learning Bayesian Statistics. And I think I butchered your name, did I?
No, it was quite good, yes.
Okay. Yes, because I rehearsed it and that didn't work. But yeah, thanks a lot for being on the show. I've been meaning to have you here for a while because you do a lot of very interesting things. We know each other from the PyMC world, but that's the first time we actually meet almost in person. So that's great. I'm very happy you're here. Thanks a lot for taking the time. As usual, let's start with your background and your origin story. Can you tell us what you're doing nowadays and how did you end up doing that?
Yeah, for sure. And thanks for having me on. And maybe next time we can meet in person for some hiking in the mountains.
Definitely.
Yeah, so my background, currently I'm in an Internet of Things lab, an IoT lab at the Lucerne University of Applied Sciences and Arts. Within the lab, I'm doing various modeling of engineering processes, but I wasn't always doing that. So I originally studied economics back in the US, and there we were primarily doing econometrics, and so like frequentist-based statistics. And then from there, I moved to Switzerland to do my master's and be with my girlfriend. And then in my master's, continued in data science. But that's really kind of when I started getting involved in probabilistic programming and Bayesian statistics in particular. And so after graduating, I essentially immediately started working in the lab at the university.
Okay, so pretty kind of a random road, right? Like this is rare that people end up in Switzerland, especially when coming from the US. Or is my prior wrong?
No, yeah, it's a bit odd, yeah.
Yeah, and so what do you mean by an Internet of Things lab? I absolutely don't know what that is.
Yeah, so pretty much a lot of things to do with you connectivity of hardware. And so when that hardware is connected to the internet to provide some sort of connectivity, and then that's kind of what you can kind of think of Internet of Things. And so like all of your things labeled as like smart devices is kind of under that umbrella term IoT. And so now everything is being IoTified. And so you have your dishwashers connected to the internet, coffee machines, and so forth. And so that's kind of really what IoT generally means.
Okay. Okay. So that sounds very algorithmic and deep learning, does it?
So, I mean, it's pretty. So within our group, we have a very widespread of knowledge. Within our group, you have people that are really specialists in networking and hardware. And then like data storage and processing. And then maybe like me more on the machine learning or data analysis side. And so for me, it's how do you analyze the data coming from various sorts of machines, whether that's manufacturing machines and so forth.
Okay. Okay. But how did you end up doing that? Because that's not what you studied, right? So
Uh,
how did that
no,
happen?
yeah, I think it kind of stemmed from, so back to my bachelor's in econometrics, doing a lot of time series stuff. And then you can kind of think in IoT, it's also a lot of time series stuff as well, because when you have these sensors hooked up to the machines, you're also logging time series. Like depending on the frequency, like 10 hertz, 50 hertz, you're logging a measurement every second, or 60 measurements every second. And so with that, you get a really nice stream of time series data. And I don't know how I exactly got kind of like brought into the IoT field specifically, but it was kind of like stemmed from, oh, hey, do you know various time series methods like seasonal or moving average and state space models and so forth? And it's like, okay, yeah, some of that can be translated from econometrics over into this IoT realm. And so it's kind of a bit of that kind of gradual shift.
Okay. Okay. Yeah, that makes sense. So a lot of time series, state space models, Gaussian processes, I'm guessing, or at least
Yep,
I'm hoping.
yep, yep.
How did you end up working on Bayes stats in particular? Do you
Mhm.
remember when you were first introduced to that, and how often do you use that in your current work?
Mhm. Yeah, so I was first kind of goes back to my bachelor's when I was doing um, the first couple statistics courses. And I just remember like when doing some very basic like regression models. And then in that course they're like, oh yeah, you reject the null hypothesis because of the p-value. And I'm like sitting there, I'm like, yeah, but who and why? Why is it 0.05? And who came up with that kind of like arbitrary metric? And it just kind of like was always unsatisfying to me. Like, oh, this is kind of, you follow this kind of like strict rule and diagram, and you kind of, oh, okay, yeah, you do this or you don't do that. And that was always kind of unsettling to me. And so from there, it was kind of like a more of a self-discovery, because there they never taught Bayesian in my undergrad Bayesian statistics. And so it's kind of like, okay, what else is out there? And that's where I came across Richard McElder's statistical rethinking, and then Andrew Gelman's Bayesian data analysis. And so that's kind of how I got more introduced into Bayesian statistics. But then in regards to how often I use it, it's pretty much every day. So almost every project that I've done in this lab has to do with probabilistic modeling in some form or another.
And why is that? So how come patient stats seem very interesting and important to your work, and what do they bring that you can't have with the frequencies framework?
Yeah, so the big thing I see in like with sensors and the IoT in general is, particularly the problems that I'm solving, is first off, you have a lot of sensor noise. So these sensors and the processes that they're measuring aren't perfect. And so, for example, like if you have a bunch of sensors on a manufacturing machine, the speeds that these sensors are logging aren't going to be necessarily exact. They could fluctuate a little bit. And then not only that, the process that it's measuring isn't always perfect. So I look at that, I'm like, okay, actually probabilistic programming is a really good kind of fit here because we can start to begin to model the uncertainty, some of the sensor noise in the process, and then in the kind of manufacturing process itself. And so being able to like quantify the uncertainty there is very powerful because it kind of lets you account for for some of the noise in the process and in the measurements. But at the same time, it's really also difficult because you can imagine that some of these settings are logging a lot of data. And so traditionally, Bayesian stat computational methods aren't very good with big data. And so it's kind of like I often see kind of in my day-to-day, like you kind of have this friction between the big data and Bayes. And so that's also kind of maybe we can talk about in a little bit, but you have that kind of friction.
Mm-hmm. Yeah, exactly. That's where I was going, and that's where my astonishment comes from. Yeah. So actually, do you wanna talk about that? Yeah. How do you manage to combine both, like this need for uncertainty quantification and
Mhm.
also intuitive uncertainty interpretation? But at the same time, also need to run the models. I don't know
Mhm.
how frequent you guys need to run the inference, but if you have a lot of data, yeah, that can be a bottleneck. So how do you thread that needle?
Mhm. So I'd say there's kind of three general, not really approaches, but maybe techniques that we do. And so the first one is probably what everyone can think of is you kind of have your raw data and then you perform just some aggregation on top, some sort of resampling to kind of reduce the size of the data. And then you just continue to apply your general, maybe MCMC on that. But then the second one is other inference methods like variational inference we've seen to be a very good fit because we have a lot of data, but we then with variational inference methods, we can apply that to that data because a lot of times you need like some sort of approximating strategy. And since we have a lot of data, we can come up with a nice sampling scheme to then use within the variational inference method. And then the last one is, yeah, luckily we do have some hardware at our lab that we can just throw GPUs at the problem. So we can use like maybe a lot of times like JAX, so NumPyro, Pyro, and use these more traditional deep learning frameworks for GPU acceleration.
Mm-hmm. I see. Yeah. So that last approach is quite nice also because you don't have to think too much, right? Like a NumPyro or PyMC model can just run out of the box on JAX and you get GPU acceleration and you don't have to do anything else. So I would say if you have the compute available, why not do that? Especially if you have to come up with a customized Variational inference scheme. And that's because that is much more intricate. And I'm curious what your experience with the different VI algorithms is. Maybe if you can give a lay of the land to the listeners, where do you see these methods and the different algorithms being useful or not, and what your practical recommendations are in a way?
hmm Yeah, so in regards to that, I've just mainly used kind of the standard implementations that NumPyro offers. So like with their auto guides and their mean field and so forth. And so when we were using those, it was primarily for like hierarchical models, and I found that out of the box they work quite well. So I haven't had to kind of go off into some other tangents to figure out which ones work or not.
For sure. Um, I know we're making a lot of effort also in the PIME system to have more VI. So there
hmm
is a lot of a lot of effort made with the Google Summer of Code on improving out-of-the-box VI, so ADVI. Also, Jesse Grabowski did a lot of work on the Laplace approximation in PyMC extras that you can use now with in conjunction with FitMap, where you can use the map estimate to initiate the Laplace approximation. There is also the Pathfinder algorithm that's already available in PyMC extras. We will have a dedicated episode about that with Michael Cow, who developed the Pathfinder module in PyMC extras. You know, people stay tuned for these. And I think I'm forgetting even one VI method that we are adding right now, but maybe that will come back to me. But there is there is active development on the PyMC side too, and I feel this is really great because I think like we've neglected in the last few years to improve that as a community, or at least to make people more aware of these different algorithms, and they can come in very handy.
Yeah. Who was it that kind of pioneered that? Because at least from an outsider, it kind of seems a bit like Pyro. Did Stan also do some?
Yeah. Stan has a lot of that. Pathfinder was developed by Bob Carpenter and his team, actually. At the beginning, it was developed as an initialization method for nuts, but they realized that actually the results in themselves were really good, and so they just released it also as a separate algorithm. But something you can definitely do also is initialize nuts with the Pathfinder results, which can be very useful. Yeah, like there's that. So Stan has a lot, NumPyro has a lot. We've had the ADVI module in PyMC for a long time now. Now it's getting a bit more love, and we have Laplace, we have Pathfinder, as I just said, and I am sure I'm forgetting one method, but that will come back to me.
Yeah.
And actually, if you folks want an introduction to these and the different methods, there is a talk I co-wrote with Chris Fonsbeck and actually Michael Cow, who was talking about a few minutes ago for PyData Virginia. And so I will put the YouTube video in the show notes and also the GitHub repo. And Chris was the one I was supposed also to fly to Virginia, but didn't find any affordable flights, so I had to ditch Chris, and he was the sole presenter. I think he doesn't hate me. He loves presenting, and he's so good at that.
Yeah, he's very good.
So So the video is awesome. He obviously did a great job presenting the material. So I will put that in the show notes, folks, because that's a very good lay of the land, basically, of what you can do with VI, what the different algorithms are. And then keep an eye out.
I think Juan also recently gave a talk in PyData Berlin.
Yeah, exactly. Yeah. That's what I was going to say. So the videos are not released yet at the time of recording, and I don't think they will anytime soon. I think they usually take about 2 months to release them. So folks, keep an eye out on the PyData Berlin YouTube channel, and then watch Juan Ardu's talk there, where he basically builds up on our presentation at PyData Virginia, and then builds on that, on top of that, and shows practical implementation of VI, especially SVI with NumPyro, with really good practical advice. So yeah, really recommend that too. This is a very good one. And actually, I'm curious if there is anything you do in particular, Gabriel, when you use VI to try and make sure that the results you're getting back are reasonably close to the posterior. Because we have these guarantees with nuts, with MCMC, but we don't with VI algorithms. And so usually something I do is train the model on fake data and make sure they can recover the parameters of interest in a reasonably close range, or for the parameters they can't, try and see if there is a pattern in the bias, and at least we know there is a bias in the model and where, and that's already very helpful because, well, if you can at least get a model running with VI, even though you know there is a small bias, I would argue this is already better than having no model because you only want to do MCMC. So, yeah, but so basically, I think this is something useful, but I am sure you're doing much better things than I am because you have more experience than me on that front.
No, not on that front, not really, because I also kind of take the same approach there. Like before kind of scaling out to like maybe a more complex model on our problem in industry, like I try to simulate what that data or engineering process looks like on simulated data, and then see just pretty much exactly what you said, kind of like how well the algorithm is kind of recovering the parameter or the posterior and is able to actually model the problem at hand. Yeah, it's funny. That's pretty much kind of what I do as well. I found that I do.
Okay, cool. So I'm not doing something obviously stupid. That's good. That is rare.
No.
So anything you want to add about VI, things you've noticed in the wild that work particularly well or particularly bad before we move on to some other topic?
Not off the top of my.
Okay. So yeah, something I really want to talk to you about because that's something you've worked on for a long time. Like this was really a masterpiece. So thank you first for doing that. And this is your re-implementation of BART, Bayesian Additive Regression Trees in Rust. So people probably know you can do BART models with PyMC in a sub-package that's called PyMC BART. And this is an awesome package. I use it whenever I can, but it has the defaults of regression trees, which is you have, if I remember correctly, you have as many parameters as you have rows in your dataset. So that means it grows pretty fast in the computational demands. So yeah, in my experience, when you start passing 200K observations, it starts to be really slow to infer. So what you did is re-implement the sampling algorithms, which is Metropolis Gibbs, I think, or something like that. What algorithm is that?
Like a particle Gibbs.
Yes,
stuff.
that's particle Gibbs. Yeah. So particle Gibbs, and you re-implemented that in Rust. So yeah, can you talk about that? Like basically, why would you start doing that? And basically give us the elevator pitch for the project before we dive a bit deeper.
Yeah, so the PyMC BART project, this really kind of, I believe, comes from Osvaldo. And about a year ago, he reached out. He's like, "Hey, we need to make this thing faster. Are you interested?" I'm like, "Hey, I'm all for it. Let's do it." But before that, I really hadn't used BART or was too familiar with the method. I mean, I was familiar with more like gradient boosting techniques, which is somewhat similar, but I did have the experience with the Rust, and so that was kind of a good kind of complemented each other. It's like, okay, I see kind of like maybe what like Adrian Sabolt's doing with NumPy and Rust. Maybe we can kind of share some of the code that he's been doing, and then use that within PyMC BART to help kind of, at least with the log probability evaluations and so forth. And so, yeah, this really stemmed from Osvaldo wanting to make it more performant, and then me stepping on board and saying, "Hey, okay, let's implement this in Rust, and then share some of the code base from Py."
Okay. And so how was the experience? Like it was Rust all new to you? How do you even start on such a huge project?
Yeah, so I do have prior experience with Rust within some data processing pipelines in the IoT lab. So the Rust part wasn't entirely new to me, but what was new was kind of interoperating with Python, having Python bindings. So that way the Python user when they call the BART code, it executes the Rust implementation. But in regards to the implementation process, essentially the approach I kind of took was, okay, let's implement this kind of essentially one for one from the Python implementation into the Rust implementation. And then from there, we can start to kind of optimize whether the different functions or methods. And then that way we can get more of a nice performance improvement instead of kind of just immediately rewriting something. Then we wouldn't know maybe like, okay, now this isn't kind of working right. Where did that go wrong and so forth. And yeah, I don't know if you want to talk about some of like the Rust specifics or the algorithm specifics or.
Yeah, maybe. So it's been a while since we talked about BART and regression trees on the show. So maybe if you can introduce the methods, the tree methods in general. You mentioned gradient boosting. We obviously mentioned BART. So maybe give us just the elevator pitch for BART and tree methods in general. And then I think it will be useful to dive into a bit more of the technical details of the algorithm to understand really how the methods work and why people could be interested in using BART and in which cases.
Yeah, so yeah, at a high level, then like you have these tree-based methods, and at like the simplest level, you have your decision tree, and so that's kind of just your logic. Like if this variable is greater than some value, you kind of go down the tree, and then you finally get to a leaf node, and that's kind of like your prediction for a target or your response variable. So building up off of the decision tree, you can have like a random forest, which is then like a bunch of those decision trees together into a forest. But then kind of even stepping up on top of that, you have gradient like boosting methods. And so these methods are really where you attempt to like learn, like you use kind of like the random forest, but you learn like the residual between the tree, the difference in the tree's predictions. And so when you start to do that, you're kind of like, it's kind of like a meta learner. You're kind of learning where each tree is doing bad at to kind of come up with a better producing or better predicting tree. And so this is kind of really more where BART is aligned with the gradient boosted methods rather than a random forest, because BART is kind of doing the same thing as boosting these gradient boosted methods. The way it's kind of assembling these trees is different. And the way that the BART assembles these trees is by taking random perturbations and then assessing the log likelihood of that tree.
Okay, yeah. Yeah, so it's closer to gradient boosting way of doing things, right? Yeah. And okay, so that's the elevator pitch. Now, when are these models particularly useful in your experience, and what is their strength and drawbacks?
So one of the strengths I think like if you want to kind of compare like BART and like a traditional maybe XGBoost or light GBM model, one of the big benefits of BART is that you get the uncertainty quantification. You have a posterior over decision trees, and so then with that you can actually stick that model into maybe other things that you want to use uncertainty for. For example, like Bayesian optimization traditionally uses Gaussian processes, but you can actually stick this BART model into the Bayesian optimization routine as well, because you also have the uncertainty there. But one of the big drawbacks with BART is that it's famously slow compared to the like XGBoost or like GBM. And so that's kind of one of the big drawbacks I see there with that method. But another nice thing about BART is that so with like XGBoost and like GBM, it's very easy to overfit on your data. And so you need to look at a lot of like loss curves and figure out, okay, hey, when do I stop training? how many trees do I use, how many learners, and so forth, to kind of stop the tree from training and stop the tree from overfitting. But with BART, it's really nice because we have regularizing techniques, so that way we avoid overfitting kind of inherently within the method. And so that's one really nice kind of pro I see with BART over the others. But yeah, the big, I'd say, con is that it's significantly slower than the other ones. And that's just for multiple reasons.
So yeah, thanks a lot. This is much clearer. So, and I hope it is too for listeners. So now I think it's a good time to dive into why that would be, like, where the bottlenecks are and why, like, what's the algorithm per se and how does it work basically under the hood, so that people really understand the models when they use that.
Yep. So in regards to like PyMC BART, we implement, as I think we stated before, particle Gibbs, whereas other implementations might implement like a Metropolis Hastings approach. And so with the particle Gibbs step, how the algorithm works is that so we generate a set of trees, so maybe 50, or in PyMC BART, you define the number of trees and the number of particles. And so, for example, you might say, okay, we want 50 trees and then 10 particles. And so now we're gonna perform a series of particle Gibbs steps. And so at the first step, we're gonna loop through all 50 trees. So for the first tree, we're gonna initialize then maybe 10 particles, whatever you define. And then for all those 10 particles, which are just decision trees, we perturb each one. Maybe we sample for a variable, a certain split value, and then another split value, and then we assess the log likelihood. And then at the end, we say, okay, hey, this particle, maybe particle 5 out of the 10, that's going to replace the current tree, which is 1. And then we proceed to the next tree. Tree number 2, we go through that same process, initialize 10 particles, perturb each one, weight them according to the log likelihood, and then replace that tree. And we continue until all 50 trees are essentially replaced. And so, yeah, that's really kind of at a high level, the algorithmic steps. It's really quite a simple process, which is quite surprising if you read kind of a lot of these papers.
Yeah, and were you already versed that much into BART and tree methods before working on that, or did you get that knowledge by working on this project?
Not really. So it was mainly knowledge from working on the project and reading the code base that Osvaldo and others did, which was quite readable, which is really nice procedural kind of line by line. Oh, this is what it's doing.
Yeah.
And so that really kind of helped with the intuitive understanding of, oh, hey, this is what the particle Gibbs is doing. This is kind of, yeah.
Yeah. And I second that. Yeah, the code base is really well done and written, and it's quite easy to start contributing to the package. So this is really awesome, because I've dabbled a bit with BART for work in baseball, and I haven't tried yet your Rust implementation, because that is very useful in baseball, because there is a lot of use cases for methods like BART, but there's so much data that you often need an acceleration somewhere. So yeah, whether it's using classic PyMC BART on a GPU, or actually using your Rust implementation and adding a GPU on top of that, that should probably be a really good boost to sampling speed.
Yeah, and I must say, one of the things that's really nice with PyMC BART is that there's several things, like really nice enhancements that we have. And so if you go look around online, a lot of the other packages are specifically for Gaussian likelihoods. So that's the first one. So you can't really model like a Poisson process or any other. The second one is that we also offer various split rules. So if you have in your design matrix numerical features and categorical features, you can pass split rules specific for that data type. And this is something that's common in other packages, that it kind of just assumes everything is a numerical value. And so that those are kind of the two really nice things I think differentiates kind of our package. But then lastly is that like we have the BART kind of random variable, and how this is embedded in PyMC. And so
Right.
you can model the linear predictor, you can model the sigma, that parameter. And so that's really
Yeah.
nice because you can build essentially arbitrary probabilistic programs with BART.
Right.
Whereas other package, it's kind of
Yeah.
you use that method, and that is the method that
Yeah.
you use.
Yeah. Yeah, exactly. This is actually a very good point. Yeah. That you can add that as a module in a PyMC model. So you could model your linear predictor with a classic linear regression, and then your sigma, your standard deviation, you could model that with a BART,
Yep.
a random variable. So this is very useful. And
I must say that recently in the current existing Python implementation, support has been added for more than one BART random variable,
yes.
which is really great and has been
Yeah.
something that's been requested.
Yeah. So you could do two different BARTs on two different parameters. So this is really awesome. In a way, that's starting to look a lot like the GP submodule. Right? GPs, you can add them to PyMC models really as you want. And you can have different GPs for any number of parameters you want in your model. And you really cannot do that with like GP packages, GP focused packages. Most of GP focused packages is, well, you can just use GPs. That's all. You cannot do anything else. And often also likelihood limits. In PyMC, you can use a GP with any likelihood distribution. In most of the packages, it's often normal likelihood, because that's often how it goes. Yeah. How is it? So I know on the BART, pure Python BART, we can use any likelihood we want. How is it on the Rust side now? Because I remember at the very beginning, you had not included yet categorical multinomial ability to use that kind of likelihood. Now, of course, I always use that likelihood, so I was like, ah, damn, cannot use that yet. But yeah, how is it right now when it comes to the likelihood, and especially the most multidimensional one, which I know much more of a pain to develop.
Yeah. So in regards to the current state of the Rust implementation, there are still some things that are implemented one-to-one, and I'm still working on that. But in regards to the likelihood, that's been resolved, so you can model multiple different likelihoods. But I think the one you were specifically asking was in regards to the different split rules, like the categorical and like continuous split rules. And that is also now implemented in the Rust implementation. But the one thing that's not yet is the multiple BART random variables. I still am working out some bugs there.
Yeah.
And so that's still something that's kind of being implemented on our end.
Okay. Yeah. Yeah. So concretely, we can do anything with PyMC BART Rest that we can do with PyMC BART, except for having more than one random variable, BART random variable in the PyMC model. Otherwise, everything is on par right now.
Yeah.
Amazing. Damn. It is cool. Yeah. Yeah. Thanks, Gabriel.
Yeah.
This is really awesome. That means now we'll be able to use that much, much more on baseball data. This is going to be super fun. And how do you squeeze that in actually? Like, is it part of your job, or is it something you do on the side? And like, maybe you have some advice for people who want to start doing some open source like we do, and they want to have some practical advice of how to squeeze that in the work and their free time, because in the end, this is really what research is about, right? Trying to push the envelope on very frontier topics, which are not only going to pay off for your project, but for your company as a whole, and a lot of other people who are going to use that afterwards.
Yeah. And so, luckily with this kind of a lot of the stuff I do at work uses these tools. And so if like our team and me see kind of like, hey, it would be really nice if we could speed up BART because it would help our problem at work. And then like doing the open source at work kind of aligns quite nicely. But if the problems are kind of aren't really related, yeah, that's kind of in my own time and so forth. But in regards to contributing more generally, I honestly, the PyMC and Bambi community is just, I think, one of the best in the scientific open source community. Everyone is very inviting and willing to help. But my advice kind of, I'd say to people starting out is don't bite off more than you can chew. Pick kind of maybe the low hanging fruit and then work your way up from there. I've found to be quite a fairly more safe approach and kind of goes better with the maintainers that way.
Yeah, that definitely sounds right, and that's what I recommend too, also to people who reach out to me. Maybe one last question on BART. Since you use that a lot in your work, what's your experience on these models? What do you find they are very useful for? Where do you see their limitations to be?
Yeah, so I've used them in two scenarios. One of them is it within embedding BART and Bayesian optimization routine, which you talk to with Max. But then the other one is specifically for a time series process that I'm going to use my hands, but like exhibits kind of like a partitioned kind of like blocky. It's not really the time series isn't continuous, but it kind of has like this block structure. So like from point 1 to point B, it has a constant value, and then the next time interval, it goes up to shoots up to another value, and then is constant for a little bit. And so this is kind of quite nice because these tree methods are essentially kind of like a piecewise linear function. Right. And so it's able to model that just kind of inherently quite nicely.
Yeah.
And so that's just kind of
like a very raw, weird time series, which is, I mean, no time series is really continuous, but it's like you don't even have enough point for it to look like it's continuous. And so the discreteness of the tree structure here is actually an asset.
Yep, exactly. Yeah. And you kind of see this come up in sensor-based time series kind of quite often, I think. If you kind of look at maybe like power profiles over time, you kind of see that kind of like block looking structure as well. And then you can kind of be, ooh, maybe like these tree-based methods might work here.
Yeah, okay. This is very interesting. I love it. Thanks. Actually, two other questions on that. What about the time intervals? Because a lot of the time having fixed time intervals is much easier to deal with. What's your experience here with BART models? Like, are they sensitive to the fact that sometimes the time intervals are not sensitive, which I guess might be the case with sensor data? Related to that, what about missing data, and what about out of sample predictions? I know it's a big question, but it's all related.
So the in regards to the time intervals, so you're saying when the time intervals are unequal, like the time
exactly.
between. Okay, yeah. So in regards to like the BART or just tree methods in general, I think they're very good for interpolating missing values because you can kind of impute that or interpolate that inherently within the tree. And so if you have like a sensor that's maybe didn't log a measurement over a certain time period, but that all of a sudden kind of comes back online and then it continues logging, with the tree methods, you do get a nice interpolation there. And so you don't really need to do any kind of feature processing beforehand. And so it's nice because that's handled inherently within the model.
Okay, yeah. So this is great. That's what I thought. But yeah, basically when there is no fixed time interval, it's like a missing data problem, right? So
yeah.
So they are very good at internal interpolation. How good are they at extrapolation? So really doing out of sample predictions. How
Mm-hmm.
does that work here?
Yep. So luckily, I haven't really had to use it for out of sample predictions in my
Really?
works.
Interesting. Yeah. Because I mean, obviously, I'm asking you that because I know tree methods are not good at it, at out
Yeah,
of sample
yeah.
predictions.
So I'm
Yeah.
glad I haven't had to use it. um, so I mean, I think that's one of the reasons why I did choose to use that
Yeah,
because
exactly.
like in particular with some of the couple of the problems we were modeling, for example, like if you have like actuator limits of a robot, that's pretty clear upper and lower bounds that you have from the engineering process. And then so you're not going to be extrapolating past that. And so with the bar, then you have a nice interpolation within these actuator limits.
Yeah, exactly. Yeah. So, and that's actually why also I haven't been able to use BART methods yet in production other than for exploring and
Mm-hmm.
teaching, because most of the time I work on actual out of sample data. So let's say if I work on players, the age of players is not really out of sample, right? All players are human, so you'll never have a player with 120 years old. But if you're looking at season, for instance, well, the years really are out of sample. And so here it's a problem. Or players themselves are out of sample. What about the player you never saw in your training data set? So that's often why I couldn't use tree methods or BART methods, because they don't extrapolate in comparison to Gaussian processes, which are really good in general at prediction, and state-space models.
Mm-hmm.
Okay, awesome. And so one last question, I swear, on BART. What do you mean by using them in optimization routines? I find that super interesting.
Yep. So in regards to the optimization routine, I'm specifically talking about Bayesian optimization. So essentially, this Bayesian optimization is a sequential optimization process where you typically have some sort of surrogate model, and that can be typically it's a Gaussian process, but it can really be any other method that provides a posterior. And I'm essentially kind of swapping out this GP, putting in the BART model there, and so using that to optimize for some industrial process. And so with the iterative method, essentially what we're kind of doing is we're training the model in the historical data, and then we're using, you don't have to get into the details, but some sort of function or generator to generate a new set of feature values or design points, and then evaluating that back with BART, and then running the loop again, retrain the model, generate some new values, evaluate with BART, and so forth. And so that's kind of what I mean generally with the Bayesian optimization. And it's just Bayesian because we're using probabilistic methods from what I can tell.
Okay, so it is your, like, BART is included in your loss function?
It's the surrogate model. So for example, so if you think about if you want to optimize the machine for like the scrap rate, how much scrap an industrial machine is producing, you probably don't know the physical, like the equations that will govern or produce the scrap. And so what's the next best thing we can do? We can turn to data-driven methods. And so there we collect data about the process. Maybe you have sensor measurements on how fast the robot arm is moving, how fast is material being fed into the machine. And then you also have measurements on, okay, this scrap was produced, no scrap was produced, and so forth. And so we use then the BART or the GP and to learn the association between the parameters governing the process and your whatever metric you're tracking. And then so now that you have that, that's kind of now your function. That's your mapping from inputs to outputs. And then so with the Bayesian optimization framework or loop, you're then kind of deciding, oh, hey, we want to optimize, we want to produce as little scrap as possible. So we're going to use this model that we just trained on to propose or to select the values that produce the least amount of scrap, if that makes sense.
Okay, yeah, I think it does. So this is not really that you are using BART inside of a loss function when doing optimization. This is
Not
something different.
Not necessarily, no.
Yeah, okay, nice. Yeah. Do you have any public writing about that people could look at if they are interested in these kind of methods?
We are writing a paper, but it's not published yet, so unfortunately, no.
Okay. Well, let me know when it is, because then we'll publish that in the LBS sphere, which, as you know, is extremely powerful in the world. You know, make sure to do that. Great. So I think it's a good summary of everything, Bart. Do you have anything to add on that? I forgot to ask you, or do you think we did a good job already to give people an idea of how they can use that?
No. So, I mean, our goal is to essentially provide backwards compatibility with the Rust implementation. So it's just a drop-in replacement. But I think the things that we maybe didn't touch on too much, maybe for some of the Rust people out there, maybe like what were some of the interesting Rusty bits that kind of resulted in some nice performance gains, I think could be kind of fun to talk about.
Yeah,
Yeah.
sure.
Yeah. So a couple of the things, or especially one of the areas that was nice to implement with Rust is in the tree proposals. And so what we do with PyMC BART is we have a prior probability over the depth of the tree. And so if you think of a binary tree, it has as you add nodes to it, then the depth of the tree will increase. And so we have a prior probability of how deep a tree can be. And you can actually set this as a user using the two parameters, alpha and beta. And so in the tree proposals, we propose a variable to split on and a value to split. And so based off of that and the prior probability of the depth of the tree, we can essentially, we then can say how likely a tree is to be grown. So essentially, how likely is it the depth to increase? And so traditionally then, in the original Python implementation, we performed in the tree proposal, we would always perform a tree proposal and a systematic resampling to propose the particle to replace the tree. But with the Rust implementation, we take a lazy approach. And so we use a smart pointer called reference counting to essentially defer or wait to essentially materialize the growing the tree until we know we will accept that tree to grow. And so we kind of like beforehand we'll calculate we'll compute the proposal, and we'll say, hey, this is what it would do if it were to be chosen or selected. And then if it is selected, okay, materialize, actually compute the results. And so it's a bit of a lazy kind of way of doing it. And so there it's really nice because in the systematic resampling, we resample according to the weights or the log likelihood of the trees. And so if you have 20 particles, and then after systematic resampling, we select like 10 of those new particles all come from the same one because it had a high weight, we essentially have to copy or perform a deep copy or a clone of that tree structure, which can be very expensive. But since we're now kind of using these smart pointers for an only copy if we know we're going to accept the tree proposal, then we get a really nice performance boost there. And that's kind of just a lower level detail that's I think quite cool.
Yeah. No, that is definitely super cool. And so if people wanna get started on PyMC BART and especially the REST implementation, what should they do? What should they look at? Should they download?
Yeah. So I think if people want to just read the code base to start helping. Currently, the code base is under my repository, and I think we can link that in the show notes. And I have several issues there where things that should be need implemented or cleaned up. But and so I think that would be a very good place to start, is just going to the repo and looking at some of the issues. I have them all tagged as good first issue and various other tags.
Yeah. So I put that already in the show notes. So feel free to look at that, folks. That's if you want to start getting involved. I was asking, what if people want to start using it? What I would advise is, and that's going to be in the show note too, go to the PyMC BART website, look at the tutorial notebooks, and then just install BART-RS and just run these notebooks, but using the REST implementation. And you'll see it's literally a drop-in replacement, except when you need to use two BART random variables, as we were saying. But otherwise, this is literally the same. And I think it's amazing. This makes it so easy for people to start. And BART models are really good because they are super flexible, they are very easy to understand, and they are usually a very good baseline if you are in a case where tree methods are applicable. So if you're in this case, practical advice would be definitely try PyMC BART, because the model is going to be super easy to write. It's going to be just like this. BART just figures out the functional form. So it's just like one BART variable, you feed that into your likelihood, and you're done. And you see how it works. If you're in the cases we talked about before where it doesn't work, well then that's going to be for next time. But if you are lucky enough to be in these kind of cases, I think it's a very good shot to.
Yeah, absolutely.
And so to play us out, Gabriel, I saw that you recently worked on some other optimization problem, which is reproducing Uber's marketplace optimization. And you have a really good blog post about that I put in the show notes. You put also all the code into a GitHub repo that is also in the show notes, folks, if you want to look at it. Do you wanna touch on that briefly? Basically, what it is, what it does, and why would people be interested in that?
Uber has a system in place that performs resource allocation. And so what their problem is they have what Uber can do is they're a ride-hailing service with a bunch of different programs like Uber Eats and your normal driving scenarios. But what Uber can do is that they can influence the marketplace by essentially allocating money to different programs to stimulate supply and demand. But this results in a business problem hey, as a company, we have a finite amount of money. How much should we allocate to each city and each program within the city such that we can maximize some sort of business metric, and such as like gross bookings, which then maybe influences the profit of the company. And so I was interested in how this even works. So how do you perform resource allocation with optimization methods? But then what I found out quite interesting was that they were embedding a neural network into the optimization algorithm to model the forecasting problem. And so you kind of have these two kind of interesting components. You have the optimization algorithm, but then the fact that they're embedding a neural network into the system to help learn the association between how much money they're allocating and how much this influences a business outcome such as gross bookings. And so
is that the same idea as what you talked about by embedding a BART model into the optimization?
Yeah. So it's kind of the same. And because I don't think a lot of people, I mean, maybe a lot of people know this, but like you can really embed like any machine learning model into like an optimization kind of program and then optimize for those features that you're using in the model. And so essentially this is kind of what I wanted to do here is like, okay, let's embed a machine learning model into an algorithm or optimization component to produce an optimal allocation scenario. But what's really interesting with the optimization algorithm used here, the alternating direction method of multipliers, is that it's a distributed optimization algorithm. And so it happens kind of in 3 steps. And so in the first step, you use the neural network to predict essentially how much gross bookings each city is going to have given a certain amount of allocation to this program. And then you select the ones that optimize that objective. And then the next step, you perform a consensus step where you are trying to get the cities to kind of agree with each other to satisfy the constraint. Typically, you have the constraint of maybe Uber can only allocate $1 million, and we need to divvy up that $1 million to each city such that the sum does not exceed $1 million. And so you have that consensus step. And then the last step is just kind of a dual update step. And then you iterate over this. And so it was really kind of a nice exploration. But I think what could be more interesting and something I talked to with Juan was, what if we embedded more of a probabilistic model into here? And so then so now we can have the entire posterior over our decision space, and we can say, hey, you should allocate like between 100,000 to 150,000 to city A and program A, B. And so that's kind of where I kind of see this going in a way, is kind of, instead of now replacing the neural network with a more of a probabilistic model to have uncertainty over our decisions.
Really cool. Yeah. It's really amazing. Really love that. Well, that's actually a public writing that we can refer people to if they are interested in this idea you were expliciting before of embedding a BART model into an optimization algorithm. I think this is very close. This is using a neural network, but this is also very, very cool. So yeah, and I definitely some application of that in the baseball world for sure. I mean the sports world in general. So yeah, this is super cool. Yeah. Thanks, Gabriel. So yeah, all the links to that are in the show notes. Any other current or upcoming projects you want to talk about before we close up the show? Something you're excited about?
So not really current projects on the plate. Maybe there are a couple previous projects where I see more probabilistic programming could be in play, but yeah, nothing at the moment.
Okay. And I'm curious also, what are you curious to see in the coming month then? Right? Like, what is it something you would really like to see in the Bayesian world, maybe, but in the data world in general, in the data science world in general, that would have a huge impact and potential on your work, or things you are able to do?
Mm-hmm. I think because I think a recurring theme of a lot of the problems I work on is optimization. And I think better tooling around embedding or using machine learning models, probabilistic models within an optimization framework, whether that's Bayesian optimization, whether that's in traditional convex optimization or sequential decision making. I think because typically now, especially at like work, I need to hand roll all of that together myself. And I think it would be really nice to have a package or a framework that really helps with that process.
Yeah. I agree. It would be something very interesting and very useful. Amazing. Damn. Thanks a lot, Gabriel. I'm very, very excited to try these new things, like the BART, REST part, and also the optimization thing. So folks, if you want to contribute to BART RS, the links are in the show notes. We're always looking for people who want to make this better for themselves and everybody at the same time. And I'm sure that Gabriel will welcome any help on that.
Mm-hmm.
Anything to add, Gabriel, before we ask you the last two questions?
No, nothing from my
Okay,
side.
good. I'll take it as a sign I did a good job. So I'm going to ask you the last two questions I ask every guest at the end of the show. If you had unlimited time and resources, which problem would you try to solve?
Mm-hmm. So I think I'm going to defer back to what I was just saying in regards to the tooling. And in particular, kind of the specific problem space is sequential decision making. And so kind of the big idea or the big pitch there is like, what decision should you take now such that your immediate action or your immediate reward is maximized, but also takes into account the future contribution, the expectation of the future contribution. And this is kind of this problem space of sequential decision making, sequential optimization is really kind of quite formal in the control theory world, but in regards to kind of like business applications, I think is quite lacking, especially in the open source world. And so developing like a library or framework for that, I think would be a great step forward for modeling sequential decision problems. That's something I would really like to work on.
Yeah, that definitely sounds like it would be very useful. And second question, if you could have a dinner with any great scientific mind, dead, alive, or fictional, who would it be?
So I already had dinner with Tommy Capretto in Buenos Aires.
And I recommended the restaurant, so I feel like I was at that dinner too, you know.
Yeah. No, but probably I would say probably Richard Feynman.
Mm-hmm.
Because I've read some of the biographies of him, and not only would it be like, I think it'd just be a fun dinner, right?
Mm-hmm.
Like,
Yeah.
a lot of technical people can be quite boring or socially awkward, but Feynman being technical and fun, I think would be for a good dinner experience.
Yeah. Definitely agree on all these accounts. But Feynman sounded very interesting and cool, and that the technical people can be what you said. So yeah, this is a great choice. This dinner is getting crowded. I can tell you, this is a popular choice. So we're gonna have to scooch at the dinner table. But we should go to Buenos Aires to that same restaurant. Yeah. I'm sure Feynman would have a lot of things to say about it.
I think so too. I forget the name of it. Otherwise, I would recommend it right now to everybody.
Yeah, me too, actually. And it's like, I don't know. I'm blanking on the name. Tommy, come to our rescue.
Yeah.
Awesome. Well, Gabriel, that was a great show. Thank you so much for taking the time. Show notes are going to be full for this one, folks. So make sure to take a look at them. And well, Gabriel, next time you have a fun and useful project like that, you are welcome anytime on the show. Otherwise, really looking forward to meeting you in person in Switzerland at some point. I am definitely going to come and do some hiking over there, which my wife and I love. Gabriel, thank you again for taking the time and being on this show.
Yeah, thank you for having me. It's been a lot of fun.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbaystats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbasedstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Loss and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbasedstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.